Everyone, I'm Emanuele De Bono from Naples, Italy, and I work in the École Centrale de Lyon in France. You may remember me for my introductory video in Smart Answer. Let's watch a short extract of it. The objective is to reduce the noise transmission through air ducts. The main example is in aeronautics, where the air duct in this case is the future generation of high bypass ratio turbofan engines, which will have to respect the increasingly more restrictive regulations on noise pollution. The inner surfaces of the nacelles are treated by so-called liners, which are currently based upon the Helmholtz resonator principle, coupled with dissipative materials. Such techniques become cumbersome if applied to low frequencies. Our smart liner consists of an array of electroacoustic cells, each one made up of a loudspeaker and 4 microphones. They are capable of reproducing the desired boundary behavior, thanks to an appropriate control architecture. Then the problem becomes to look for the best boundary behavior which would reduce the noise transmission in the air duct. The boundary condition assuring the total acoustic absorption for any angle of incidence is not physically realizable. An interesting boundary condition was conceived by Dr. Collet and others, which could be implemented in our array of cells by discretization. So let's check if these 3 years have brought some fruitful results. Let's consider an air duct, where air must flow inside, but we want to stop noise to propagate. Of course, we cannot put obstacles into our tube, which would impede also the airflow. We have to allow air to flow, but we need to stop the noise to propagate. Then, we can only work on the boundary of our duct. It is the general problem of acoustic liners. The classical liner techniques are too thick to attenuate the low frequencies. There comes the semi-active liners, which are capable of enlarging the possibility of classical liners in lower and broadband frequency ranges. A semi-active liner is an array of electroacoustic cells. Each cell has a loudspeaker, the actuator, and 4 microphones, the sensors, as we see in the picture. On the left, we have a view of the interior of the duct lined by our electroacoustic cells. By measuring the pressure and controlling the electrical current in the loudspeaker coil, it is possible to reproduce the desired acoustic behavior, that is the impedance, on each speaker. The local pressure on each cell is retrieved by averaging the 4 microphones measurements. As function of the pressure, we inject the electrical current in the loudspeaker coil such that to achieve the speaker acceleration which would assure the desired acoustic impedance on the speaker itself. The first strategy for the liner control has been called boundary local impedance control. In this equation, we can see how the pressure and acceleration are related through the local impedance called Z local. This is how a typical local impedance interacts with an incident sound field. Part of it is absorbed and part is reflected. A more interesting approach is the boundary convected impedance control. This strategy involves the measurement not only of the local sound pressure P, but also of its first x derivative, dP dx, where x is the longitudinal duct direction. The characteristic of this boundary convected impedance control is that the boundary reaction is convected along the tube longitudinal axis against the coming excitation field, with a convection speed equal to the coefficient Ca appearing in the equation. In this figure, you can see the experimental test bench adopted for our tests. We have 2 upstream microphones and 2 downstream microphones which are needed for the evaluation of the noise transmission through the air duct. The section treated by our electroacoustic liner is in the middle. Good. We are only left to experience by our own ears the noise reduction achieved. A broadband noise between 200 and 900 Hz is coming from the upright opening of the duct, and this is the noise registered by microphone 1 upstream the lined segment. By applying the boundary local impedance control at the microphone 3 location downstream the treated segment, we register these. It it is evident the broadband noise reduction achieved thanks to our electroacoustic liner. Let's now check the effect of the boundary convected impedance control strategy. So, microphone 1 upstream and microphone 2 downstream. The reduction of the noise transmitted downstream is highly enhanced in this case with respect to the simple local impedance control. Another funny result achieved by the boundary convected impedance is the break of the reciprocity principle. First of all, what is reciprocity? Well, it is a very intuitive concept for which in acoustics, for example, if the source and receiver position are interchanged, the noise getting to the receiver will not change. This concept in acoustics has equivalence in solid structures, the Betti-Maxwell theorem, and in electromagnetics with the Lorentz theorem. Again, let's audibly check this so-called break of reciprocity. First, the source is at the bottom left opening of the tube. So let's play microphone 3 first, the one close to the source. Then microphone 1 on the other side with respect to the line segment. We don't hear much of a difference, do we? Now, if we put the source at the other end of the duct and listen to microphone 1, now close to the source. And then microphone 3 after the lining area. It is very much attenuated as already seen before. Such technique for reciprocity breaking is based upon the bias introduced on the boundary, that is the convection of the boundary reaction we have seen before. For both local and convected impedance control, care must be given to the stability of the entire system. As the control is implemented on digital signals, time delay happens between the input and the output of the controller. This reduces the stability margin at high frequencies and therefore constrains the performances of the semi-active liner. In the video we see the effect of the acoustic feedback by placing a rigid surface in front of the electroacoustic cell. It can become unstable. It's the well-known Larsen effect in it. Nevertheless, a porous material which is a good absorber at high frequencies could easily restore the stability. That's why we came out with a simple but efficient solution to increase the stability margin of our electroacoustic cells. A thin porous layer, the pink one you see in the picture, in front of the speakers allowed for more ambitious performances of our controlled liner. Such techniques are now under testing in heating, ventilation and air conditioning systems, as well as in the nacelle inlet of turbofan engines. Thank you very much for your attention, and if you are interested, please stay tuned on the next demonstrations.